Today we are going to do two experiments. One is your maximum power transfer theorem, another is transient response of series RC circuit. So these two experiments are there. And, we are going to. So please open the LTSPICE at your end.
Yes, sir.
In that time, I'm opening whiteboard. I have uploaded the notes on LMS because LMS they have means ready for this. So you can get the notes or tutorial from there now. Okay.
Okay, sir.
So the next topic is maximum power transfer theorem. And suppose that if you have any circuit, so it is maximum power okay. So according to this, suppose that if you have a circuit like this, you have a 10-volt source, resistance of 10 ohm. Again, you have a resistance of 10 ohm and then 5 ohm. If you connect a load resistance RL here, then according to maximum power transfer theorem, if you replace this circuit by the Thevenin equivalent of this, it means that the Thevenin equivalent voltage VTH and Thevenin equivalent resistance, that is RTH. Then if you want maximum power to be transferred from this side of the circuit to this side or to the load resistance, then the maximum power transfer will take place when the value of RL is equal to RTH. And that maximum power transfer or P maximum will be what? VTH square divided by 4 RTH or RL, whatever you write, because after this condition only you can say that this is maximum power transfer. Now we have to prove this on LTSPICE because we have to verify this on LTSPICE. So what you have to do now, you open the LTSPICE. I am opening the starting a new. I'm opening new file here. So what I can do, I didn't save. Anyway, okay, I'll do it later on. So you have to go to the components here. You type voltage VOLTAGE. So you'll get this. You have to press OK, and the voltage will come. Then you press escape. You select resistance here. Control R. Then again Control R. So I'm assuming that we have calculated the RTH. That R1 is RTH here. So I'm taking very simple circuit. You can take somewhat complex circuit just like this also. Means you can have this circuit. So you can try with this circuit also. As of now, I have taken only I have assumed that you have the VTH and RTH, and I will vary the value of RL, and then we'll check for different value of this RL. How the power which is means we will calculate across this load resistance, it will vary according to that. So that we will verify. In this case, now we will make the connection. We need to take the ground also. You can by the help of this wire, you can make the connections. So this is the circuit part. So this is the circuit which is there. Now we will use the numeric value, means what is the magnitude of these terms. So here I'm using a 10-volt source. In this case, I can use a 10 ohm resistance, and I will vary this resistance. Suppose that initially I have taken a resistance of 5 ohm. Okay. Now you can use the labeling also. Uh, there is one labeling option also that I. So this is your V no, so VL. Okay. And similarly, you can give here. This is your V in input. Okay. What you have to do now, you have to we have to simulate this, right? So when you simulate, we want to obtain the DC operating point. So I am using this, and now these are the values of the various parameters in this. If you see here, you can plot a graph like this. I'm showing you. You just I am varying the load resistance, that is R. Initially I had taken 5, then 10 and 15. Then I am calculating the corresponding voltage. Okay. So corresponding to 5 ohm load resistance, it is your RL. 5, you have a voltage of 3.33. If you see in the LTSPICE, the value V at V1 is what? 3.33. Okay. So this is the voltage. Now the direction of current, in this case, they have like assume negative, but means it depends on the convention which they have used, but you can use it positive sign here. So the current in this case, it will be how much? 0.67. Okay. So what is power? Power is voltage into current. So corresponding power in watt will be what? 3.33 into 0.67. When you multiply these two terms, you will get 2.23. So this is the watt. Now, if you increase the value of this, if in this case, if you increase the value of this load resistance to 10 ohm, and then you again simulate this, so you will find that the value of voltage has increased to 5 volt and the value of current is 0.5. So if you put the value here, when the load resistance is 10 ohm, voltage is 5, this is 0.5, so you have the power of 2.5. Okay. Similarly, you can obtain, we can increase the value of this to 15 ohm, and then you simulate this. So your voltage is 6 volt and the current is 0.4. So here 6 volt 0.4. So when you multiply, so you can see here also that when the value of RL is equal to 10 ohm, that is RTH, because if you see in this circuit, RTH is what? 10 ohm. So when the value of RL is equal to RTH, this is the, you are obtaining maximum power, right? If the value is less than RTH, then the power is less. Here also it is less when the resistance load resistance value is more. So you can say here that when the value of RL is equal to RTH, you are obtaining maximum power in this case. Okay. So this is your proof of maximum power transfer theorem. You can take some more readings here, like you can take 1 ohm, you can take 20 ohm, so that 5-6 readings should be there, so that you can visualize in a better manner. Okay. So this is your maximum power transfer theorem. Understood?
Yes, sir.
So this is what you have to do for maximum power transfer theorem. Now let me save this. Okay. Now the next theorem is transient response of series RC circuit. Next experiment is, so this is experiment number 3, right?
Yes, sir.
So this is experiment maximum power transfer theorem is experiment number 3. Similarly, not similarly, but the another theorem is not theorem. The other another experiment is basically what you have to obtain the, you have to study the transient response of series RC circuit. Okay. So in this case, what we will take a, either you can have a DC voltage. Generally, when we teach in the theory part, we say that you have a DC voltage and then you have a switch here. Okay. Then you have a resistor and capacitor. Suppose that the resistance value is 1 kilo ohm and capacitor value is 10 microfarad. So time constant, basically there is one term that is called time constant. Time constant in this case is what? It is the time in which the, suppose that if it is 5 volt, okay, it is the time when your when you switch on the circuit, then it will take some time to reach from 0 to 5 volt. 5 volt is the maximum value. This is the 0 volt. This is with respect to time. So when you switch on this, so it will take some time for this circuit to go from, let me make it clear, from 0 to 5 volt. So the time it takes to go from 0 to 63.2%, 63.2% of the maximum बोले तो 5 volt. So that is called transient, means time constant. So tau is what? The time taken for this voltage to go from 0 to 63.2% of the maximum value or steady state value is your tau. That is time constant. Generally, it is said that it requires around 5 tau time. So here you require 5 time constant tau to go from 0 to the peak value of the DC signal which you are giving here. Okay. In the LTSPICE analysis, instead of taking, because we are not using a switch or something like that, we will use a pulsed signal here. I will give a pulse signal here and I will connect it directly with the circuit. So because it is, and then we will observe the pulse within this duration. Okay. Whether it is means within, we will calculate the time constant within this duration. So that we will do on the LTSPICE. Understood? Any doubt in this?
No, sir.
So now we will go to the LTSPICE and I think that, okay. In the LTSPICE, again, what we will do, we will take a, first of all, a resistor, press Ctrl R, you rotate this, escape. Then you take a capacitor, escape. You take a voltage source, escape. Then we will take a ground. Now we will connect them via wire. You have to connect this here. Okay. Okay. So what we will do now, we will make this as 5 volt, but we will go to the advanced because we want to give a pulse signal. So we will give a pulse signal where the initial voltage is 0 and the final value is 5. We are not giving any delay. Time on is 0.1 second and time period is 0.2. Okay, so this is the pulse signal which we are giving here. You can move this, how to move this.
और ऊपर बार में एक ड्रैग का ऑप्शन है. नेक्स्ट.
Oh, okay, this is doing something else. अरे पूरा ही गड़बड़ हो गया.
आई गेस कंट्रोल Z से वापस ही आ जाएगा. सिर्फ पल्स वाले पे एक बार क्लिक कर दो तो शायद वो मूव हो जाएगा.
I will give again the values. So this is 5 volt. I will go in the advanced pulse 0, 5 on. This is 0.2 second. Okay. So what we will do, we are giving input signal, a pulse signal, which is having maximum value 5 volt. The time on period is 0.1 second and time off is 0.2. Now we'll simulate this. Okay. Because we are doing the transient analysis. So here the stop time I am giving 1 second. Okay. So now we will try to. Okay, we need to give the value. Sorry, we need to give the value also here. So here I am giving 1 kilo ohm, 1K. And the capacitance value is 10 microfarad. So you have to write here 10 U. Okay. Now we'll do the simulation. अरे भैया बहुत ज्यादा आ गए तो. How to close this? Want this to be anyway, leave it. So now we will simulate this. Now we want to obtain the voltage, right? So across the capacitor. So this is how it is looking like. Whatever the input voltage you are giving, if you want to take that as a reference. So if you see here, it is taking some time. It is not steep slope. It is taking some time to go from this here to here. Now your input signal is from here. So this is your input signal. If you zoom this, or you can see here also that now you can check by yourself that what is 63.2% of 5 volt. It will be 3.15. Okay. So when you go here and you move the cursor, I think here. So here I will try to make it within 0.1 second, right? So that we can obtain or we can zoom it and we can do this analysis in a good manner. So I will go for this. So you can see here that within this we will try to obtain this. So here at 3 point, how to move this? Yeah. So here we want to obtain the value at 3.15. So the horizontal, vertical. Horizontal. So what I want to say that we need to obtain the value at 3.15. We need to check that this should be value. This value should be around 10 millisecond, because RC is basically here 10 millisecond. If you see here, what is the value of RC in this circuit? Where is the circuit? You multiply R with C. So this is 1 kilo ohm. This is 10 microfarad. Okay. So this is 10. So 10 into 10 is by minus 3. So it is around, oh, okay, 100 milli. What is the value of this? Can you check? RC in
1
this
by
case,
RC.
RC is the time
1000
constant, right?
into 10.
So 10 raised to power 3 into 10 raised to power minus 5, because it's 10 microfarad, right? So this
10
will
raised to
be
power
10 raised to power
minus
minus 2 second. So I can say that this is how much? 10 millisecond. Okay. So the RC here. Now what is RC definition? That it should 5 volt का 0.63 से multiply करिए. What is the value? This is 63.2% of the peak value. 0.632. What is this value? So if you multiply 5 with 0.632.
3.16.
So 3.16 is corresponding to the on the time axis. If you are here on in this plot at 3.16, you should be able to obtain the time here around 10 millisecond. Okay. So what we will do here, we will do the analysis corresponding to this only. And how to move this? I forgot actually. Okay, it is moving. That's good. So around 3.16 we have to check. 3.16. So here it is coming out to be 15.4 millisecond. Okay. So now what we will do, we will, because practically it's not completely transient. We need to have, means we need to give some values, because ideally the response is step, but it is not practically. So what we will do, will in the analysis part, will give some rise time. Suppose that if the rise time is 0.001%, and fall time is also 0.001. So what is the response? Let's check. So we'll simulate this and then we'll try to obtain this again. If you, okay, in the horizontal axis, if I give this, I want to obtain up to 0.1, na? 0.1. So this will come here, and I want to move this as 3.16, near 3.16. So it is almost near 10 millisecond, right? So when we have assumed a practical system where there is 1% rise time or fall time, because that will happen. So you are able to obtain around 10 millisecond RC or time constant. So this is almost accurate. Now, if you decrease it further, here, if you make it 0.01, you will be more closer. Suppose that if your system is perfect, then, and I simulate this again, obtain this one. And in the horizontal axis, I want to observe only one pulse time, 0.1. Okay, now I will just move this further down. So here it is almost 10.068. So it is almost perfect means evaluation of this state, right? So now you can see here uh, uh, that we are able to observe the rise time. Now you can vary the value of the resistor and capacitor. Then you vary your own time means, because when you vary the value of R and C, the time constant will vary. And you can check on your own, you can study on your own how by the variation in the resistor and capacitor, the rise time, sorry, the transient response is changing. Okay, the time constant will change. So you study by yourself. So this is how you have to, means these are the two experiments which you have to perform on your own. And if you have any doubt, you can ask me. Okay.
Okay, sir.
So that's it for today. I have recorded this session so that suppose that if you got stuck, you can listen to this recorded session